When an operator presses and releases stop, the S, TR1, and R coils are de-energized, and their associated contacts immediately return to their deactivated states. Both primary contacts open, and the de-energized motor free spins to a halt. The timer relay resets, as does the entire system. Finally, let's consider soft starters making use of timers. You'll recall soft starters initiate conduction at a predetermined start voltage and smoothly ramp up to full voltage over an adjustable ramp-up time, T-up, for a soft start. During the run phase, full voltage is applied to the motor. Following loss of the input signal, soft starters can also smoothly ramp down voltage to 0 volts over an adjustable ramp down time, T-down, for a soft stop. A timing diagram of the soft starter output and input signal might look something like this. Advanced soft starters and motor drives executing a soft start or soft stop function may also include additional contacts that give feedback about the state of the soft starter or motor drive and can be used to coordinate the timed activity of soft starts and soft stops. Consider a soft starter that has 3 associated contacts. 1. SS hold, that asserts itself when the input signal is being asserted, as would a regular control relay. This one can be used for holding contact purposes. The 2 others execute time-based shifts. 1. SS run, that only asserts itself when the soft starter is in the full voltage run mode, and another, SS active, that asserts itself whenever the soft starter is active, either in ramp up, full voltage run, or ramp down. When overlaid with each other on the timing diagram, they might look something like this. Note how the input signal relates to the 2 feedback signals, SS run and SS active. If you think about it, they're both in effect executing timer functions from the perspective of the input signal. Without explicitly stating it, SS run is executing the on delay function, and that only after a measurable period the input has been asserted does SS run transition to its opposite state, this time delay being the adjustable ramp-up period, T-up. The moment the controlling input disappears, SS run returns to its deactivated state. SS active, in contrast, is executing the off delay function. The moment the controlling input is asserted, SS active enters its activated state, however, maintains the activated state for a measurable period after the controlling input has disappeared. This time delay being the adjustable ramp down period, T-down. Although not explicitly stated, SS run can be considered an on-delay timer with respect to in, and SS active can be considered an off-delay timer with respect to in. To further enhance the functionality, and admittedly complicate things, these contacts can also have normally closed and normally open sides. Let's examine a couple simple scenarios how this time-based feedback about a soft starter's run and active states can be used to coordinate a reduced voltage starter. First, let's examine a soft starter that needs to be bypassed in run mode. Soft starters have 2 important utilization categories. Soft starters categorized as AC53A soft starters are intended to indefinitely carry full primary current, and those categorized as AC53B soft starters must be bypassed after the soft start event and be given a chance to cool. Bypassing an AC53B rated soft starter with the use of an on-delay timer is essentially the repeat of the technique utilized in both the primary resistor and part winding reduced voltage starter method, with one minor exception. This time we're assuming the soft starter itself is capable of acting as a timer and generating the on-delay function. In this case, one of the normally open time-closed contacts associated with the SS run output. Although not explicitly drawn as a normally open time-closed contact, SS run is in fact executing the on-delay function. Given the soft starter itself is capable of generating this delayed transition, it frees this system from coordinating 2 independent devices, notably a separate timer relay with the soft starter. When employed in this ladder logic diagram in primary schematic, note that the R or run contactor should bypass the AC53B rated soft starter during the full voltage run period, yet allow the soft starter to do its thing during a ramp up or ramp down event. Let's walk through the ladder logic and see how this works. At startup, the soft starter receives power. Note soft starters, since they're solid-state devices, ordinarily need to be constantly powered up to run. Note the placement of the e-stop and overload contact. When the e-stop and overload are in their normally closed state, the soft starter receives full pilot voltage and is powered up and ready for use. If either of these devices open, the soft starter would be completely depowered. This is critical to the functionality of the system during an emergency shutdown or overload event, which would disable the ramp down period and completely halt conduction. Additionally, note the placement of the manual motor starter immediately upstream of the soft starter serves to disconnect the soft starter from primary voltage for repair or troubleshooting purposes. When an operator presses start, the input signal is asserted. The soft starter immediately initiates conduction at the start voltage and initiates the ramp up time. The SS holding contact immediately changes states and establishes a holding circuit, which allows an operator to release the start push button. Note, however, the SS run contact executing the on delay function does not immediately close, but only after a measurable delay period, notably the T-up ramp up time. After this time period has elapsed, full voltage is applied to the motor, and the SS run contact closes. The R contactor coil is energized, and the R primary contactor closes, which bypasses the AC53B rated soft starter. Full voltage is applied to this motor, and the AC53B rated soft starter is given a chance to cool. When an operator presses and releases stop, SS hold and SS run immediately return to their deactivated state. However, the soft starter initiates the ramp down period, where voltage is progressively reduced from full voltage to 0 volts over the adjustable T down period. Note, when the R contactor coil is de-energized, the R primary contactor is opened, which allows the soft starter to conduct the deceleration period. After this time period has elapsed, the soft starter returns to a ready state. Again, note that the e-stop or overload would serve to completely depower the soft starter in the event the motor needed to be stopped during the soft stop event. Moving on, let's now consider an AC53A rated soft starter that does not need to be bypassed. However, it's making use of a friction brake. Recall from the reduced voltage starters with friction brakes lecture, available at the Big Bad Tech channel, I briefly introduced this functionality, so this might be a review. As previously mentioned, we're assuming the soft starter itself is capable of generating an output, SS active, that is asserted whenever the soft starter is active, either ramping up, applying full voltage, or ramping down. If you think about it, SS active is executing the off delay timer from the perspective of the controlling input, although it's not explicitly drawn this way in the ladder logic diagram. When employed in this ladder logic diagram and primary schematic, note that the friction brake should be removed the moment the soft starter initiates conduction and remain removed until the soft starter halts conduction. Note the primary schematic incorporates a B primary contactor and brake coil above stream of the soft starter. When the B contactor coil is energized, the spring-set electrically released brake solenoid experiences full line-to-line voltage, and the friction brake would be disengaged. Let's walk through the ladder logic and see how this system works. At startup, the soft starter is completely powered by pilot level voltage. An operator presses the start button, which asserts the input signal. The associated contacts SS hold, SS active immediately change states, and the soft starter initiates conduction at the start voltage and the ramp up. The closure of the SS active contact energizes the B contactor coil. The B primary contacts close, which energizes the electrically released brake. The brake is disengaged the moment the soft starter initiates the ramp up time. Given a holding circuit has been established by SS hold, an operator can release the start push button. Once the ramp up time has elapsed, full voltage is applied to this motor. If an operator presses and releases stop, the input signal disappears and the SS holding contact opens. However, the SS active contact executing the off delay timer function remains closed, ensuring the brake remains disengaged while the soft starter executes the ramp down action. Voltage is progressively reduced from full voltage to 0 volts over the adjustable time period T down. Once this time period has elapsed, the soft starter halts conduction and SS active opens. The spring-set friction brake is engaged and the motor is brought to a halt. Again, note that the e-stop and overload serve to completely depower the soft starter and serve to override the ramp down action, immediately depowering the motor. Alright, that's about it for reduced voltage starters with timers. In conclusion, this lecture took a brief look at timers used to coordinate the orderly transition from start to run mode for several different types of reduced voltage starting methods. We observed that the on-delay timer can be used to open or close one or more contactors a measurable time period after some input has been asserted. Additionally, we observed that the off-delay timer can be used to keep one or more contactors opened or closed a measurable time period after a controlling input has disappeared. By no means are these the only suitable applications of timers and timing functions. However, they are extremely common and useful applications. We'll examine other applications and other timing functions in later lectures. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.